Every so often, astronomy hands us a moment that forces us to rethink what we thought we understood. A quiet signal, a subtle measurement, a faint displacement of light, and suddenly a new reality opens. This week, that moment came from Mars. A spacecraft orbiting Mars, equipped with imaging instruments far more stable and sunlight shadow isolated than our Earth-based platforms, has achieved something extraordinary. It has measured the trajectory of 3I 2017 U1, our newest interstellar visitor, with 10 times the accuracy previously possible. To the general public, that might seem like a technical detail, but to those of us who model interstellar dynamics, who analyze the fine print of celestial motions, this is enormous. When you map an object's path with that degree of precision, you are not simply predicting its position, you are reading its story, you're learning where it came from, how forces have acted on it, and whether it behaves like a natural object or not. And when that object is moving through our solar system from another star, every decimal place matters. This measurement, this quiet gift from an orbiting eye around Mars, reshapes how we think about planetary defense, interstellar debris, and even the possibility of technological artifacts drifting between the stars. It also gives us a new opportunity to study an anomaly with unprecedented clarity before it disappears forever into the dark. Trajectory is biography. It's the one thing an object cannot fake. Every known force in the universe, gravity, radiation, plasma, drag, outgassing, magnetic fields, leaves fingerprints on a traveling body. For most comets, these signatures are familiar. They deviate in predictable ways because sunlight evaporates ice from their surface. The recoil from these jets pushes the comet gently off its gravitational path. But 3I 2017 U1 is not most comets. Before this Mars-based measurement, its motion already showed hints of non-gravitational acceleration that didn't match the physics of a typical icy nucleus. Some of these deviations were subtle, too subtle for Earth-based telescopes plagued by atmospheric distortion and Earth's own orbital motion. But from Mars, the geometry changes, the parallax shifts, and the observational noise drops dramatically. Where Earth sees a wobble, Mars sees a line. And that line, that precise arc etched across the Martian sky, shows that 3I 2017 U1 is experiencing forces we cannot yet fully explain. The most conservative explanation is unusual outgassing, yet the comet is outgassing at distances where ice should not sublimate. The least conservative but still scientifically valid explanation is that we are witnessing physics we have never modeled before. Either way, this measurement is not a trivial update. It is a revelation. Science progresses by confronting anomalies, not ignoring them. The Mars orbiter's refined measurements show a persistent directional acceleration that does not fit the standard equations used for natural comets. When plotted against time, the deviation has a smoothness that surprises me. Natural outgassing is chaotic. It fluctuates as patches of ice heat unevenly. But the 3 Atlas shows a pattern more akin to a continuous force, as if the source of acceleration is steady, not sporadic. Could this be due to a deep reservoir of hypervolatiles that vent in a stable pattern? Perhaps it could be caused by unfamiliar interstellar materials whose thermal response is unlike anything observed locally. Also possible? Or is it like Oumuamua before it, demonstrating behavior reminiscent of a thin sheet, a light sail-like object experiencing radiation pressure? We do not know. But now, with 10 times better positional accuracy, we can begin ruling out the impossible and focusing on the improbable. In astrophysics, improbability is often the birthplace of new knowledge. Planetary defense is not merely about stopping impacts. It is about understanding the cosmic environment that surrounds us. For most of human history, we assumed the greatest threats came from local asteroids, fragments from our solar system's formation. But the appearance of 3 interstellar objects in less than a decade changes the landscape. If interstellar debris is more common than we believe, then Earth's planetary defense models must adapt. Why? Because interstellar objects have higher velocities, unpredictable chemical compositions, and non-gravitational forces that differ from typical comets, with trajectories that can shift in ways we cannot yet model. If even one interstellar fragment traveling at tens of kilometers per second were on a collision course with Earth, the warning time would be drastically shorter. That is why precise trajectory mapping is foundational. The Mars orbiter measurement is not merely academic. It is a demonstration of a new architecture for global safety and a multi-Linnet observational baseline. Earth sees one angle. Mars sees another future. Missions around Venus or Jupiter could see yet more. With 3 or more observation points across the solar system, we can triangulate interstellar objects with unprecedented accuracy months sooner than before. In other words, Mars has just given us a glimpse of the future of planetary defense. Let me be clear, 3i Atlas is not on course to hit Earth. The significance lies in what this measurement teaches us. If I were standing in front of a camera right now, I would say something like this. This new measurement from a spacecraft orbiting Mars reveals something profound about our relationship with interstellar objects. It shows that when we expand our vantage point beyond Earth, we gain clarity not just in astronomy, but in understanding our cosmic neighborhood. By mapping the trajectory of 3i Atlas with T-fold accuracy, we have taken the first step toward a solar system-wide early warning system, a network that can detect, track, and analyze fast-moving objects from other stars. This is not science fiction, it is a natural extension of how we protect our planet. The more precisely we track these visitors, the more we learn about their composition, their origins, and the processes that sculpt them. Some may be natural, some may be unusual, and in rare cases, a few might even challenge our assumptions about technology in the universe. But whatever their nature, one thing is clear: the cosmos is not silent. Objects from other stars are passing through our solar system more often than we imagined. If we are wise, we will treat each one not as a threat, but as a message from a distant system written in ice, dust, and motion. The Mars measurement is only the beginning. Over the next few months, NASA and the ISA will refine their models. Ground-based observatories will attempt to detect micrometeoroids. Radar arrays will search for metallic content. 3i Atlas may vanish into the dark soon. We may never see it again. But its trajectory, that thin, precise arc measured from Mars, will remain as a blueprint for the future, a future where Earth, Mars, and perhaps one day, the moons of Jupiter work together to watch the skies, not as isolated worlds, but as a multi-planet civilization, because that is what this really means. The Mars measurement is not just a scientific achievement. It is an act of cooperation across planets, a quiet, profound step toward humanity becoming a species that listens to the galaxy instead of merely existing within it. And for me, that is the greatest discovery of all. And thanks to a spacecraft orbiting Mars, we now understand its path with extraordinary clarity. The universe sent us a message, and for once, we were ready to receive.